structures. Many of you have been through this. We did this in regular chem. Okay, we did it much more extensively in honors, but we did do it in regular chem. So Lewis diagrams are named after the guy that kind of developed these. And Lewis diagrams help us determine how these atoms are going to bond. And what you have to do is you have to start out by knowing how many valence electrons you have. So remember, that's the 1, 2, and we skipped our D block, 3, 4, 5, 6, 7, 8. We don't need to worry too much about 8 because they're already taken care of. Okay, so that is our Lewis structures. And then we do electrons around those. So for carbon, there's 4 electrons. We always make sure that we have them distributed evenly before we double up. So 1, 2, 3, 4. And then if there was more, like for oxygen, we would go 1, 2, 3, 4, 5, 6, or 5, 6.
Yeah.
Okay, either one's fine.
But you can't do, what is it called?
You can't do, well,
you have to fill each little
yeah,
side before
we typically won't have this if the oxygen's just sitting by itself. Okay.
Yeah, but if it's with a thing, a charge.
Yep, we'll talk about that.
You had like a side in the bottom and then the top and the other side.
Yep. Okay, so Lewis structure shows a representation of how the atoms connect to form a molecule. We have to account for all the electrons in the molecule, and we can't bring extras in unless we have an ion. So like our polyatomic ions, we can have an extra because it has a charge. A line indicates 2 shared pair of electrons, and that would be a single covalent bond. 2 lines is going to be a double bond. That's going to be 4 electrons. And 6 electrons, which would be 6 dots, would form a triple covalent bond. We can also have lone pairs of electrons. So for example, nitrogen has a lone pair of electrons. They're not going to bond to something there. Okay? So if we had ammonia, this would be what ammonia would look like. These are going to be shared electrons, and this is called a lone pair.
And you can draw lines for those.
Yep. You could do it like this.
I think that looks sweeter.
Yep.
Looks better.
There. Okay. So you can do that as well.
Yay.
All right. So how do we draw these? We determine the total number of valence electrons. And I showed you how to do that. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. We draw the skeleton structure. That's going to place a single bond between the atoms and the starting point. The atom needs to make the most bonds to fill its octet is usually placed in the center. This is usually the least electronegative element.
That's genius. Okay, that's important.
Hydrogens and halogens have to be terminal. They have to be on the end, particularly fluorine and hydrogen. Okay? Elements in the 3rd period are capable of expanding their octet to share more than 8 electrons. And this is something new that we did not do in regular chem last year.
Oh,
What?
We didn't have expanded octets in regular chem.
you know how sulfur got the weird, crazy stuff
Yeah.
going on?
Yeah,
Had,
that's
like,
why.
an extra bond.
Yep.
Yeah.
Okay. So we are going to place the remaining electrons as lone pairs so that we can fill as many octets as possible, starting with the most electronegative elements or the ones on the outside, and we work our way in. If we run out of electrons, then we add double or triple bonds as needed. And honestly, you are just going to have to just do a bunch of these. Okay. This will not come naturally to you until you've done some. Okay. So you're just gonna have to practice, 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 practice. And then all of a sudden it'll go. And you'll be like, oh, this wasn't that bad. Okay.
Genius. Okay.
You guys remember that from last year where you're like, oh yeah, this isn't bad now.
It still never clicked for me. I don't know why.
Well, you're
Probably
gonna
the same
practice
way.
some more this year, so maybe we'll get you there.
I'm just like, this is so genius. What a genius topic.
Okay.
I'm like,
So, step one. Step one, we are going to find how many valence electrons we have. So for carbon, it has 4. For hydrogen, it has 1 each times 4 of them is 4. And oxygen, there's 1 of those times the 6. So 6 plus 4 plus 4 is 14.
So how come they didn't do 1 in the parentheses?
I don't know. I don't like that.
Oh, but it's the same thing.
Yeah. Here, this is the electron. Well, yeah, it is the number of electrons. Yeah, this is the number, how many you have.
Yeah, but like, why didn't they put just 6 for oxygen?
Yeah, they should have had a 1 here, and then this in 4, and then that went. 4.
Yeah, they're not very
There.
genius.
Okay, they were not consistent. I'm sorry.
Thank you.
Okay,
I don't appreciate it.
so out of these, carbon is going to go in the middle. Now, hydrogen is less electronegative than carbon. Why did carbon go in the middle? No.
It needs more for its octet, or the octet.
How many does hydrogen need? 1. It needs 1 more to make it 2. Hydrogen always has to be on the end because it can't have, if it has a bond here, it can't bond any other way. It doesn't have any spots
Unless it's
to gain. So hydrogen has to be on the end because it can't hook up with anything on the other side of it.
so.
Okay. So then we look at the next least electronegative element, and that would be carbon. So that's why we throw carbon there. Now, I can't throw the hydrogen here and throw the oxygen over here. Why?
Because
H can't have 2. So that's why they had to throw the oxygen there and then throw the hydrogen coming off of it.
Okay.
Okay. So here we've got our skeletal structure. We count up our electrons at this point. 2, 4, 6, 8, 10. We are not up to 14. Well, carbon can't accept anymore because it can't expand its octet, and it's already at 8. So that leaves oxygen. Oxygen still needs 4 more to complete its octet, so we throw those guys on here. Okay, does that make sense? Okay. Here's my, again, this should have been a 1 times 4. This is going to equal 4. This equals 2, and this equals 6 to total up to 12 electrons. So here, again, carbon's in the center. We're going to put these around and make our skeleton. We're going to count our electrons. 2, 4, 6. That means I've got 6 more left over. Okay. I'm going to add those to my oxygen. So I've got those added in. But the problem is if I put those all on oxygen, I can't get my carbon up to 8. Carbon needs to be at 8 once it's shared everything. So I'm going to have to take these 2 electrons here and bring them here. Now if I do my totals, hydrogen has 2 and 2. Carbon has 2, 4, 6, 8, so it's good. And oxygen has 2, 4, 6, 8, so it's good. These are like little jigsaw puzzles. Yeah.
The notes say hydrogen and halogen have to be on the ends. What is a halogen?
Halogens are the things in column 17. That's their names. So column 17 up here.
There's 7 with you.
Yep. Yep. So those are called your halogens. You may have heard of like halogen lights, for example. Okay. The ones in the last column, their title is called noble gases. You'll sometimes hear them referred to as inert gases, but that's noble gases. So we'll use that term a lot too. The ones in the first column, except for hydrogen, are called alkali metals. And the second column is called alkaline metals. And you may have heard of those in terms of batteries a lot of times. Okay, good? Okay. Now, there are some exceptions. Nitrogen is not an exception. Anything that is a non-metal, so silicon all the way over to chlorine, your arsenic all the way over to bromine, your tellurium, iodine, and actually xenon can form bonds with expanded octets, just to kind of blow your mind. I know. So those can expand their octets and go into the D sublevel and make bonds. So those can be expanded octets. So for example here, sulfur. If we had sulfur, sulfur is going to be in the middle because it's obviously less electronegative than fluorine. Fluorine's the most electronegative. So we would come out, we would put our bonds around here. So we would have our 6 bonds. Then we would count up our electrons. And we would go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So forth and so on. We'd end up with 48 electrons and everything would be happy. Because at that point, fluorine would have 8 and sulfur would have more than 8, but that's okay because it can expand its octet. James, you look like you're in pain.
It's so weird that they just
Yep.
more.
Yeah, they just go whoa,
That's so genius.
right on the extra.
All
right. Coordinate covalent bonds are another thing that we can do where instead of just sharing electrons, like one from the, here we've got like in this bond, we've got one from the carbon coming in here, and we have the oxygen supplying the other ones over here, okay? When we look at coordinate covalent bonds, what happens is one of the atoms provides both electrons for the bond. So that's happening here. So here, those bonds, okay, here the carbon's bringing in these 2, the oxygen's bringing in these 2, this one and this one. So the oxygen's actually supplying 4 electrons for this triple bond, and the carbon's only giving up 2. So these are called coordinate covalent bonds. They can be used in order to form these octets. And like I said, they're not shared equally. Something's bringing more to the party than the other one. Also, boron is another exception. Boron is said to have an incomplete octet. Boron is happy with how many electrons? 6. Okay, so boron's happy number is 6 electrons. Okay, so that is another exception that you kind of need to be aware of. No, it just means, you know how these, I always talk about how they need to be happy. They need 8 to be happy. This one's happy with 6.
Can it have 8?
I don't know. I would have to do some research on
So if we
that.
ever use it, it'll only have 7.
I'm guessing, yeah. Just don't get tricked by it. I'm trying to prevent some of that. All right, here we go. So I'm going to put my, and the other thing about this is your formulas are written typically in order from least electronegative to most. So if you're like, which one should go in the center, just pick the first one listed in the formula. Because that's how formulas are created for the most part. So I'm going to put my carbon here. I'm going to link it to another carbon. Then I'm going to find my hydrogens, and I'm going to go, okay, a hydrogen has to be on the end. Has to be on the end. I'm going to hook this one up here. And that's my 3 hydrogens, and I've got a chlorine. I need to figure out my electrons. I had 4 times 2 is 8. I had 3 times 1 is 3, and 7. So I have a total of 18 electrons for this guy. Yeah.
How do we draw the thing where it can be, the double bond can be in multiple places?
We're not to resonance yet, honey. Just give us a minute. Okay. So here we have our so we've got 2, 4, 6, 8, 10 electrons. How many more do I need to do? 8. Okay. So I'm going to go and I'm going to fill up my chlorine. Okay. So now my chlorine's filled up. I still have 2 electrons to place. So I could put one here and one here. What is my problem? There's an issue here. Right. This carbon only has 7 electrons, and this one only has 7 electrons. They need 8. Can I add an extra electron here and here? No, because I've only got 18 to play with. That's all I've got. Okay, this is a budget that you have to stick to. You can't just go out and take out a loan and loan out an electron. Okay, so what are we going to have to, how are we going to manipulate these 2 electrons to make them work for us? Right, we're going to double bond them. So what I'm going to do is I'm going to drag this electron over to here. I'm going to drag this electron over here, and I'm going to form a double bond. And there's my double bond. Now, if I do an inventory, hydrogen's good, hydrogen's good, hydrogen's good. Carbon has 2, 4, 6, 8. This guy has 2, 4, 6, 8. And this guy has 8. So everything's happy. We're done. Now, what Ben was asking about was something called a resonance structure. You can draw resonance structures. When you do that, you have to kind of use an arrow here. And this could have 4 possible resonance structures. Why? This chlorine could go here. It could go here. It could go here. Or it could go here. So we could redraw this with the chlorine here and a hydrogen here. We could redraw it with a chlorine here and the hydrogen there. Or we could redraw it with the chlorine here and the hydrogen here. Okay. All right. Any questions on that guy before we move on to the next one?
So the first element is usually the next one.
Yep. Typically listed in order of electronegativities. There are a few examples of exceptions. This is one of them. Here, nitrogen is more electronegative than hydrogen. This is just kind of the way that they have done this for a long, long time. This was like one of the chemicals that they messed around with back in the old alchemy days. And so, you know, they didn't really pay attention. They didn't even have anything called electronegativity back then. So it's just kind of a nod to that whole era. And that's kind of the way it got written back then. And they just haven't changed it. But this is more electronegative than hydrogen. So, but typically, not as a hard rule, but as a generalization, your less electronegative element will be listed first in a formula.
Not bad.
All right, let's try to draw some Lewis structures here in our redo. I'm going to do my inventory of electrons. All my carbon will supply how many electrons? 8. And my hydrogen will supply 2 total for a total of 10 electrons. So I'm going to draw my 2 carbons here, and I'm going to draw my 2 hydrogens. I guess I'll draw one here, and we'll throw one over here. Okay, how many electrons do I have placed right now? 6. Can I put any more here? No, hydrogen can only have 2, so they've got to go here. So I could go doot, 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 and place 6, but I've got a problem. Right, I can't do that because this guy will not have enough electrons. So what I have to do with these is I actually have to bring them in, and like she was saying, I have to triple bond. And a lot of this will come from you just practicing. It's going to be a practice, 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 practice.
Okay.
All right, let's talk about this guy because he's got something new on him. What does this mean here? He has an extra electron hanging on. This is one of your polyatomic ions. We're going to count up our electrons. My oxygen here has 6. My hydrogen is going to give us 1. This negative charge is going to give us an extra 1. So that is a total of 8. All right, I'm going to draw my oxygen. I'm going to draw my hydrogen on it. Then, so that I can't double bond. Hydrogen cannot double bond.
You have to do the 6 on the little dude.
Yep, this is one of those. Yep, so this is where, yep, we have it like that. So that's my 8 electrons. This is my extra one that was brought in. Now, I have to indicate that I have an extra electron there. This is where the square brackets come into place in your drawing, and you put a negative out here.
Oh, yeah.
So you're telling the folks that you have this extra electron right here by putting that negative sign right there.
Okay. Need 36. No.
All right, I have 14 here. I have 4 here. And I have 6 here for a total of 24 electrons. Okay. I have 2, 4, 6 here. 8, 10, 12, 14, 16, 18. So I have, between these two, I've got 16 placed so, no, 8, yeah, 16 placed so far. I've got 18 there. Okay. I need to get carbon built up. Okay. And I also have to get sulfur with all of its necessary electrons. So right now, how many electrons do I have placed on here? I've got 8, 8, and 8, guys. 8 times 3 is 24. So I've got all my electrons placed. I still have a problem. Yep. Carbon doesn't have 8 electrons. What do I do? What do I do? Okay, do I double bond it with a fluorine or with a sulfur? It has to be the sulfur. Fluorine cannot double bond under any circumstances because it cannot expand its octet and it only can receive 1 more electron. So fluorine always has to be on the end and it cannot double bond. So no, chlorine is in the next row. It could expand its octet, but fluorine cannot. So there is how we would draw that guy.
Okay.
All right, what's special about this one? Boron. Okay. So it has how many electrons that it's bringing to the party? 3, and 21 is 24. So I've got boron here. Remember, it is one of those special reduced octet elements. So I'm going to do my chlorine around here. Then I'm going to do 2, 4, 6. This is 8, 10, 12, 14, 16, 18, 20, 22, 24. That's how many I had to spend. I've spent them all. I'm at a 0 budget. We're good. All right. Sulfur is 6. Fluorine is 6 times 7, 42, for a total of 48. And I had already done this one back in the notes a couple slides ago. So you can see what that guy would look like if you just want to reference that. And then we can move on. Make sure that I've got everything covered for today. Yep, I have. Okay. So you will find today that you have 2 5 and 2 5A in your homework packet for this weekend. So it's like actually like 4 pages. So you got quite a bit to do. Okay. And then next week we're going to get into more on that resonance and the formal charge. Formal charge, when you come back, when you check your answers, you may have something slightly different than mine if you don't remember what formal charge is. If you do remember what formal charge is, then go ahead and use it. Otherwise, you might end up with slightly different structures because you don't know formal charge yet. And that's okay. We'll get there. I just don't want to try to dump too much onto your plate between now and then.
This is a lot.
Yep. But it should go pretty fast. Okay. All right. There you go. In